Hello, good afternoon. Welcome again to a new food4Rhino webinar. Today we have the pleasure to have with us Ján Pernecký and his colleague Eva. Ján is going to present a new plugin called Monoceros, and this is for discrete assembly for architects and designers. It was created at Studio Subdigital for computational design using the wave function collapse algorithm. And Monoceros is used for optimally occupying an envelope with discrete modules, where the spatial relationship between those modules can be constrained by a set of user-defined rules. Well, I guess Ján will explain this much better during the webinar. Ján is together with Ján Tóth, one of the makers of this plugin. And in 2015, he founded and taught Research Sessions, a platform for online teaching of computational design tools, Grasshopper, processing, etc. He has organized many meetups with Research, many conferences, and he has taught at many universities in Italy, Poland, Spain, Slovakia, and Czech Republic. He has also been a guest professor at Studio Brno, Czechia, also at the IAC and many other universities. In 2016, he founded Subdigital, and this is the place where this plugin has been created. This is a studio aimed at digitally enhanced design. And his colleague Eva is today also with him. She can also take a look at the chat. Remember, you can place your questions at the chat you have on the right side of your screen. And then I will pick all of these questions. And at the end of the presentation and live demo, we can ask Ján, and I guess he will have time to answer anything that was not covered. Again, this webinar is being recorded, so right after it finishes, it will be available on this same link. And well, I hope you will enjoy it. Ján, many thanks for being here, and you can start now if you want.
Thank you very much. Thank you for having me. Also, thank you for the introduction. You basically said everything that I wanted to say as my own personal introduction. But nevertheless, I will summarize all these things. I will share my screen now. Some of you might know me as a teacher of many Grasshopper tutorials. Together with other colleagues, we had a brand called Research Sessions. And this is how the website still looks, but we are slowly transiting the whole education thing to a new brand that Eva is running, which is called ArcSys. And you can get all the existing tutorials and all the new ones that we are putting together at arcsys.com. ArcSys is a new platform for putting together all the knowledge about the computational design, networking, skill building. And what is very interesting is that this is a female-driven company, and I'm the only one that is somehow different from the main stuff. But that makes things very dynamic. As I said, that research sessions are now transiting and being almost over. We moved all the education part of research to ArcSys. But also we started a company with my colleague Ján Tóth that is called Subdigital. And I would like to invite you to our website, www.sub.digital, where we are having most of our work published. And Subdigital is the place where things are being created. So on ArcSys, we are teaching, on Subdigital, we are creating, and we are doing all sorts of stuff. We say that we are materializing the digital age, but basically we are applying the computational design, the parametric design, all that we've learned in academia into practice in jobs for real clients. We put together a website where most of our projects are being published. There are all sorts of projects. Some of them are presentation objects that are very interactive. There is a lot of hardware software behind. Some of them are spatial architectural, like this exhibition. Some of them are pure design, like these two projects. Some of them are functional design, like this one. And one of them is also Monoceros. At the beginning of the website, you can see something that we call Subdigital book. That's basically a PDF with all our projects. We would be very happy if you had a look and gave us some feedback. Now, I should move on to Monoceros because that's why we met here today. Monoceros is a plugin for Grasshopper, but not only that, it's also a much larger project that we started at Studio Subdigital about a year ago. We call it Project Monoceros because it's kind of a big thing already. We also are putting together a book, which is maybe a little bit old school format, but we believe that this also works. I will show you the book through this session a couple of times. But again, I would like to invite you to see the website. You can find it on monoceros.sub.digital. And you can find all the information about Project Monoceros there. What happened about a year ago is something that you can see on this picture. In our studio, we are 5 people. 4 of us are architects and designers. 1 of us is a programmer. And we invited interns to our studio, 4 of them. And together we said that now it's time to redefine our own course in the computational design, and we identified the discrete aggregation as the next big thing that we should be working on. And we wanted to share with the community because this is also sort of a community project, because we started developing it in this setup with the students, interns, and also with professionals. And that's how Monoceros started. We spent 3 months prototyping not only the tool itself, but also the narrative behind, and also the design that you can achieve with this sort of an approach and tool. And this is what you can see on the website here. There are examples of projects that have been done with a very early stage of this methodology. I think there's very few that use the current optimized version of Monoceros. We originally called the method and the tool WFC. I will explain very shortly why. But also, in case you already have some experience with Monoceros, and if you already have some project that has been made with Monoceros, please let me know, and we will add it to the collection of projects here on the website. Meanwhile, you can have a look at the other projects. These are not only the projects that were made during the period of development last year, but also these are projects that people started publishing after Monoceros was actually published. So Monoceros is a plugin for Grasshopper. It only works for Windows versions of Rhino. That's because it uses a library that is highly optimized, and we were not really properly able to optimize it for both platforms. So if you want to try Monoceros, please install the Windows version of Rhino 6 or 7. It works on both. I don't know, we've never tested for Rhino 5, but maybe it also works there, but there is no reason to go back. You can download Monoceros from food4Rhino. Also, you can download Monoceros using the package manager in Rhino 7. Also, you can use these automated ways of installation. When you open an example file in Rhino 6, it automatically downloads Monoceros for you. So I will go back to the website, and one very important thing that you can find here is, before I go there, I will also mention that Monoceros is completely open source, and you can see the source code here in 2 repos on GitHub. The first repo is Monoceros itself, which is written in C#. The other one is the core solver for Monoceros, that is a wave function collapse implementation that my colleague Ján Tóth made, and both of these libraries are freely available. So I made this public because when I was learning myself how to write the Grasshopper plugins, the best source of information for me were different projects where I just had a look into the source code and just tried to understand how this works. So that's why we decided that we should also make this a public contribution to everyone who wants to write their own plugins for Grasshopper. Now, the very important thing that I want to show you is the user manual. The user manual is something that I started writing right after I published the first version of Monoceros. It is already a super long document that you can read. And I think that there's all the important information written here. But at a certain point, I decided that it's already too long, and I stopped writing it. But we didn't stop developing Monoceros. So now Monoceros is much bigger than what you can see in this user manual. But still, whatever you can read here, it's still applicable, it's still true, but there is way, way more than this right now. The good thing that I believe there is with the documentation is that you have some example situations where you want to achieve something. You will find it in the heading. You will read what you will achieve with this exercise. What is the logic behind? Then you have a picture where you can see the Grasshopper definition. You see the result, but you can also download all the files. So all of the examples for Monoceros here are also downloadable. But still, this is certainly not enough to learn everything there is about Monoceros. We are still learning ourselves because it opens a completely new paradigm for computational design. So when you scroll down, you have also the frequently asked questions. That's something that explains how to start, what is the good exercise, what the error messages means, and so on. But even if this is not enough, then I would really like to invite you to the Ultimate Monoceros workshop that we are putting together with ArcSys. And you can also find the link here on the website. It's going to take place online on 27th to 30th May, which means next week, Thursday, Friday, Saturday, and Sunday in the afternoon hours, European time, so that we make this accessible to also people who are working. It is an extensive workshop with many hours of teaching, lecturing, giving tutorials, individual consulting and desk crits. You can read everything here on the website. I believe that you will find also the links in the chat and on the YouTube video link. And also we have to announce that for people who are watching this tutorial, there is a 21% discount. The discount code is McNeel21 with all capitals. We will also put the discount code into the chat. I already believe that it's there. So we can discuss the workshop at the very end. I really do want to show you what Monoceros is and how to start with it. And then we would like to also show you some extra things about the workshop. So now, what is Monoceros? I will use the help of the book that we are putting together. My colleague Kristina Uhrova is making the graphics of the book. So kudos to her. And I will show you what this is. Monoceros is a plugin that allows you to make discrete aggregates. The discrete aggregates are assemblies, geometrical architectural design objects that are made of smaller parts. The parts, we call them modules. And the modules, they somehow connect to each other, but in a logical way. And the aggregates that we are putting together with Monoceros, they connect in a very precisely defined way. So Monoceros is solving to fill an envelope, whatever shape you want to fill, with modules that you predefine. The modules are something that you can manufacture out of real materials, metal, wood, or whatever you want. You can connect them together using certain connectors, and Monoceros fills the whole envelope with these modules in a meaningful way so that they actually meet and connect the way you want. This is based on an algorithm that is already pre-existing. It's called wave function collapse. And it's been around the architectural research for maybe 2 years now. It's quite a new algorithm, and it was not made for architecture. It was originally made by Maxim Gumin, a software developer, game developer for game design. And this is serving mainly to actually create maps for computer games in a meaningful way. So when you have a path, the path has to continue. When you have a sea, the sea has to have a seashore, and so on. So this is an algorithm that makes this really possible and pretty quick and fast. It became very famous, the algorithm, with the games published by Oskar Stolberg, who is, again, a game developer and a digital artist. His game called Townscaper is very well known, and it's really beautiful. and it works with the same algorithm. And Oscar has a lot of other games, or maybe rather toys for computers that use the same algorithm for different purposes. We decided to take the algorithm and make it accessible to all the designers so that they can take the use the benefits of the wave function collapse for architectural design. And I will show you how does it work and what does it mean. Monoceros and all the discrete assembly processes, they understand the space as discretized, chopped into chunks, into blocks. We call the blocks slots. So what you can see here is like a chessboard or a puzzle that is at the beginning, it's not, it's empty, or rather completely full. I will explain in a moment. And you need to fill the chessboard with certain modules, objects, in a meaningful way. And this is how it actually works internally technically, but I will use pictures as a simpler explanation of what is happening here. So at the beginning, your task is that you have an envelope, a space that is discretized, chopped into blocks. In our case, they are squares, but I will explain that with Monoceros, they don't have to be squares, but for simplicity, we are showing squares. So you have a chessboard that you need to fill in with certain modules. So the modules, those are the small pieces that you put into that chessboard. In our case, we've got 3 different modules. One, let's call it water or sea. The other one, let's call it a land. And the third one is a seashore or a coastline. Just an explanation in Monoceros, when you want to rotate something, it's a different module already. So a coastline that would be vertical would be a different module. So we've got 3 modules. Logically, if you think about what can be the neighbor of each of these modules, for the seashore on the bottom, it can be only a seashore. I'm now speaking about the sea itself, the water. So next to the water on the bottom, there could be only the water, because the land, it would need to have the coastline. The coastline, again, on top, that's land. So you cannot put land right next to the sea. The same applies to the left and right. And on the top, there can be either another tile filled with water, or there could be already a coastline, this one. So there are 2 options here on the top. When it comes to the land, it's the opposite. On the top, left and right, there can be another piece of land. And on the bottom, there can be either a land or a coastline like this one. And when it comes to the coastline, on the top, there has to be just the land, because the water, that wouldn't fit. Another same piece of the coastline, that wouldn't fit. So only the land would fit. And on the left and right, there can be another coastline. And on the bottom, there has to be, again, the sea. So we've got the modules, and these are the rules, the local conditions, local neighborhood adjacency rules. So connection rules, you can call them. So what wave function collapse, the original algorithm in the core, in the center of Monoceros, what is it doing is that initially it doesn't really take an empty envelope and fill it. It actually does the opposite. It takes a completely full envelope, where in each grid cell here that we call a slot, so these are slots here, each slot at the beginning offers a possibility to place any module. So in each of these slots, you can have either the land or the sea or the coastline, and you don't know which one should you place. What wave function collapse is doing, it's removing the options as you start putting the modules into the slots. So in the first step, it is called an observation, which is a metaphor for physics, but that's not important here. In the first step, the algorithm puts one random module somewhere, and in our case, it's here, and the random module from all the possibilities inside of that slot, it picked the coastline. And in the next step here, it looks around at the neighbors, and according to the rule set, it removes the options that are not available anymore. So once you put the coastline here on the top, you cannot have, it's impossible to place the sea anymore, because that would be against the rules here. It's impossible to put another coastline up here, again, against the rules. And the same applies to the left and right. You cannot put the land and the sea here. You can only put the coastline here and here. And on the bottom, you can only put the sea. So this is a cleanup of the slots of the envelope. So we made a decision for this slot. Then we looked around and propagated the change and made the change to these slots. And from there, we just grow the change here and here and here. And the same applies next to this one that is already decided. There can be on top, there can be only the land. On the left, there can be only the coastline. On the bottom, there can be only the sea. And the same applies here. So the change grows and propagates throughout the envelope. And at the very end, you end up with a solution, which happened because we removed the options. And this is called a constrained modeling or constrained programming. You're adding constraints. At the beginning, you're unconstrained. You have no limitations. You add more and more limitations until there is a solution. It all depends on the decisions that you make along the way. This is made automatically, and this is just one example of what can happen. Another example could be something like this, and let me show you here. I will come back to the previous slide just in a moment. So we've got the same modules, we've got the same rule set, we've got the same initial state envelope, but we make the first decision, the first placement of the module is different. So we put a C in this position. So when we propagate the change, when we clean up the possibilities, it's clear that on the left, right, and bottom, it's only possible to put another sea tile, the water. It's impossible to put a coastline here because that wouldn't fit. It's impossible to put a land here because that wouldn't fit. So this is clear. This is sure what has to be placed here, but it's not so sure up here because the rules, they actually only remove one of the options, and the option that was removed was dry land, and there are still two options remaining here. So there can be either another coastline or there could be another tile of water, and we don't know yet. So let's propagate the change. Let's just grow and see what has to be changed. So in the next tiles, now in the next step, this is clear. There has to be water here. There has been a decision to put water here. And here it is also clear that only water tiles could be placed. But up here in these two positions, again, there are still two options remaining. And also this tile is a neighbor of something that has changed, and we need to look there as well. But there is no change whatsoever, because if another tile of water is going to be placed here, that allows placement of another water and coastline. But if this happens to be eventually the coastline, then there is an option to place another dry land tile here. So we still have three options here. Let's propagate on. It's again here, it cleans things up for us. There are only two options remaining here, but the neighbor of this tile is here and here. And it's still, because this allows everything, it still allows everything here. So nothing has changed, and we don't have to, because this one didn't change, we don't need to propagate here. And the same happens here, and so on and so on. So at the end of this cleanup stage, we end up with something like this. At the bottom, it's clear that there can be only water. Here, there can be either water or coastline. Here, there can be anything. And we need to make another sort of a random decision. So that random decision is called an observation. We've got it here. And you see that from this clean state, we need to make another random decision. We randomly picked one of the options remaining for this slot, because there could be either a coastline or a sea. So we picked the coastline here, and that's our final decision. And then we need to propagate the change. So now it's clear that on the left and right, there can be only another coastline, and on the top, there can be only the dry land. So we make the change here, that's clear. And then we look around and do the same decision making. So here, the only option that remains is the coastline. Here, the only options that remain are the dry land and so on. And at the very end of this, we've got a different solution. So with the same rule set, with the same initial state, with the same modules, we can have different solutions based on the random decisions made along the way. But all of these solutions are completely valid. I think there is another example here. I'm not going to go through that one, but again, you see you made a different decision here, and the solution is different here. So I will come back to this image. Just a moment, I need to cough a bit. That's better. So this slide shows that the modules themselves and the envelope with the slots, they can be basically anything geometrically. They could be just these colorful areas, or they could be numbers, or they could be some structure wireframe, or it could be a map. It doesn't matter. All of these 4 examples are exactly the same with different representation. What matters is the rules that we have, the geometry inside of the modules. That doesn't matter so much. So this is what wave function collapse is doing. And that's basically what Monoceros is doing as well. Monoceros makes this accessible and easy to use in Grasshopper. And you can read more here in the book. But I will just very briefly tell you that we've got three things that are 3 data types in Grasshopper implementation of Monoceros. One of them is a slot. Slot is the grid cell that we are going to fill with certain module. The slot is a cuboid or a box. It doesn't mean that it has to be a cube. It can be one of the sides can be rectangular. So the X, Y, and Z dimension, they don't have to be the same. It could be like 1, 2, and 3. They also don't have to be orthogonal. They can be rotated, but all of them have to be the same. And they can form any sort of a shape. So it doesn't have to be a box anymore. Like in the basic examples, it could be a discretized sphere, which is chopped into the slots, or anything basically. Even it could be a surface, or it could be something that doesn't have a volume. Another data type that we have in Monoceros is called a module. And a module is basically what you put into the slots. And a module is a slightly more complicated thing because it's got a cage, which is exactly of the size of the slot. And inside of the cage, there is geometry. In Monoceros, it doesn't really matter so much what the geometry is, but if you make smart choices for the geometry, it makes your life much easier. I will show you in the example just in a minute. What we do in Monoceros, which is an extension of the original wave function collapse algorithm, is that the module, it doesn't just have to occupy a single slot. It can occupy more than 1 slot. So in this example, there are 3 slots occupied with 1 module. And basically you can have any shape. It doesn't have to be in a row. It could be an L shape. It could be basically anything like a Tetris block in 3 dimensions. As long as it's continuous, it cannot have gaps, it cannot have islands and so on, so that it holds together. But this is how we fight the blockiness of Monoceros. But at a certain point, we also like it a little bit. So we keep it in our examples. But with Monoceros, you don't have to make only things that look very rectangular. And the last data type that we have is a rule. And this is the crucial part of the whole thing, because the rule, the connection rule, the neighborhood rule, the adjacency rule, whatever you call it, that's something that defines how the modules, how do they assemble next to each other. And if you look at the cage of the module, it has at least 6 sides. We call the sides connectors, and the connector, all of them have to connect properly to the next one. And you can define the connection rules in various ways. What is very important to say is that each connector of a module can have 1 or more rules that describe them. So it means just like in the example with the sea, the sea could have a neighbor of another sea above, or a coastline. So there are basically 2 rules with 1 connector. And this is what makes it really interesting, because there is not only 1 viable solution for the Monoceros setup, but there could be more. And you see, we demonstrate or render the connection rules with these lines, and it says, basically, I will zoom in a little bit. So it says that, for example, this connector at the bottom here can connect either here or here. So there are 2 options. And The thing is that with Monoceros, to make a valid configuration, you always have to describe each connector with at least one rule. So if there is no rule, no description, then there is no solution. So each one has to be described. One thing that maybe could be a little bit too much of a detail here is that each module has to be described. The modules, they don't rotate. And it's also impossible to place an empty module, when there is no option, it doesn't place an empty module and you need to make it manually, but we would do it in Monoceros quite easily. So I will close this down now, and we've got 15 minutes roughly to give you a very quick intro to what Monoceros is. I will just show you something a little bit more advanced that I'm not going to go into details. This is something that I'm putting together for the major Monoceros workshop that we are having. Just to show you, these are my modules that I manually designed or drew. So you see that it basically has a roof. It has some full module here as a wall. It's got a window. It's got an empty module. You see that it's written there. There is a wall here. This is a two-dimensional thing. And I've got an envelope here that looks like this. And yeah, so this is the envelope that I'm filling with these modules in a meaningful way. I will show you the envelope like this. So this is the discretized world. I will hide it here. And Monoceros Solver, it gives me different various all valid solutions for filling the space with these modules according to the connection rules. And when I just change a random seed, you see that it gives me different random solutions with the same rules. Some of them are completely different. It looks like a mountain resort, or it looks like a house like this one, but all of them are viable, all of them are good. You see that it's super fast. It's as fast as it gets. But this is also a super simple example. I will show you a very advanced example, which is this one. This is way more modules here, but still it's not that many. I will also show you how does it look with Grasshopper. So there is a couple of modules here. There is a couple of rules defined with these lines. Again, this is not that many if you think about what does it do. And this is the result. It fills the box with modules so that it actually makes some sort of a sense. I will show you with the clipping plane, how does this thing look inside. I already think that this is quite exciting because if you think about how to design this manually, you need to design a shape of these blocks so that they perfectly fit like a puzzle to each other. And that's really not easy. We tried with the summer school, we tried to mimic this manually and just to model things that Monoceros can do without Monoceros. And it's really very complicated. But when you use the clipping plane and look inside, it looks something like this. It generates this sort of a three-dimensional maze where everything fits, like there is no empty gaps here. There are walls, there are doors, there are railings, there are staircases. There is no vertical, like a balcony without a railing, so you will never fall. And you see that the whole setup is really very complicated. And Monoceros can do this for you really, really fast. Even if I change the envelope, the solution would be found quite fast. And when I say fast here, it takes about 3 seconds to generate the result like this, which is kind of a success, I think, with the number of modules that we have. But also I have to say that sometimes Monoceros could find an invalid solution, and then it has to try again. And it does it automatically, that's fine. But sometimes when the setup is really complicated, like this one, for example, it takes really long, many attempts to actually find a valid solution. And in this case, it took about 200 attempts, or maybe even more, to find this solution. And each solution is a couple of seconds. So eventually to find this solution, it took maybe 20 minutes on my computer. But once it's found, I can remember what is the setup that works and save it. And then it takes 2 seconds. And even if I reopen the file. But this is an extreme. In most of the cases, it's almost immediate, so you can animate the solutions. So this is also what I do here. I can really animate the solution, but this is very ambitious here. So I will be very, very quick now because we've got 10 minutes left, and I will show you the very basic setup, how to use Monoceros and how easy it can be. Even maybe before I do that, I will show you how does it look in Grasshopper, this big setup that I have here. And I will also explain to you which parts are basically unnecessary for Monoceros. So I will zoom out, and it looks kind of big, but here, what I have in this group, that just generates the railings. That's something that I can draw manually, but I was lazy to do it manually, so I used Grasshopper to make railings. Another thing that I have here is some sort of a testing, so this can be also omitted. I don't have to use that. So basically what I do here, this is a very generic setup that I use for most of my projects. So the first thing that I need to do is I need to import all the geometry that I want to use as modules. That's what I do here. And then I need to put them into their cages and generate modules, which is this part, which is kind of short. This is not so short because it's kind of universal, but it could be basically 3 components. Another thing that I need to do is I need to create the envelope into which I'm going to place the modules, which is something that I do here. And it's 1, 2, 3 components, and that's it. This is something that I'm not using now. You see that this is a dead end. That was for my testing. And then I need to define the rules. And now this has become really, really simple with Monoceros. And this is undocumented yet, but it works really well. So all the rules that I have in the setup are basically defined with 1 component only. So that makes things super simple. And then I made some fine tuning, and the fine tuning is done here. The rest is the solver itself. And then this shows the solution super quick here. Although it doesn't probably look like that on the first sight, but I will show you how easy it could be here on this example. So let's say I will show you what the result of this one would be. So the result would be something like this. We have modules or geometry that looks like this. You can think of them as pipes. And this is an example that is called pipes, and you can download it from the website as well. So imagine that these are pipes, and you want to assemble them in a certain way. And I will switch on preview of modules, which is here. And also, I'm sorry, I will draw the icons here. And also I can hide the rule preview so that it's kind of clear. So you see that, for example, this module, it's called module 10. It's got this geometry inside. This is the cage of the module. And yeah, and I've got a couple of modules like this here. Then there is a double module like this one that consists of 2 parts, and this one. This is the ending of the whole thing. So this is something that you have on top and bottom. And then we have some straight connections here and straight pipes and so on. And it basically gives you a result that looks like this. Everything is perfectly connected. There is no open end. So all of these pipes, they create certain loops. Maybe if I bake it, we can see that this is also kind of interconnected. I'm not going to do it. I will rather show you how to generate something like this. Also, another thing that I can do is I can change the envelope, which makes things a little bit more complicated, but I will show you anyway. It works because I tested this example, so it should work. So I can say that, oh, it doesn't. Never mind then. It's just, oh, I need to enable this thing in this example, and it will start working. It takes a while to find a solution because sometimes the setup is so complicated that it takes a moment to do that. I hope it will not be more than a very short moment here. Yep. Okay, it didn't find a solution. We can increase the number of attempts, but nevertheless, I will show you. Maybe I can do it on the background. If we try a little bit more, it gives you, it has more options to find the solution, and also a very complicated setup. But it works with the example that I have here. So yeah, super fast. It's different from the previous solution because I changed the rules. I will change the rules so that on the top there can be only this this U shape. So Super quickly, how does it work? So I will start a new document. What we need to do is we need to reference the pre-existing geometry that we are going to use as modules. So I will just set multiple geometries like this. Yeah, so I've got them here. I will use bifocals so that you see what components I'm using. So in Monoceros, there is a component that I always discourage people to use. It's called slice geometry, but I'm going to use it for simplicity now. It basically allows you to define modules and slots easier. What we need to do is, let's see, how do we define a module? A module can be constructed like this. And you need to define the module name, the module geometry. We already have the geometry. We need to define the base plane and module part diagonal. Module part diagonal is basically the dimension of the slot of the envelope. And I know that these pipes are 100 units big. So I will make a vector that is 100, 100, 100, which is the dimension of the grid. So this is the module part diagonal. This is the geometry. I need to actually graft this whole thing so that each one of these is becoming a separate entity. Base plane, I'm not going to explain now. Module part points, that's something that defines the cage. So because the geometry is independent from the module, you can define the cage that is smaller than the geometry and so on. This is quite important when you need to make connectors that are sticking out of the cage. So we need to define the points that define the basic cages. For simplicity, I'm just going to use the slice geometry, which is kind of a tricky component, but it gives us points like this, and I can use these points to actually define the center points of the module cages. And I also need to give names to the modules. So I will just count to I don't know how many modules do I have. I will just measure how many modules, how many geometries I'm having here. Flatten. So this is going to be a counter. It gives me numbers from 0 to 15. And these are going to be the names of the modules. So I do it like this, and I need to graft here. And yeah, it has to be text. Sorry, not this one. It has to be this text. I usually do something like concatenation so that I call them module something, but yeah. So this is fine. So now we have the modules, and you see that the modules, they have their cages, they have their geometry inside, and there are some numbers here. And the numbers, they are numbers of the connectors. Connectors are basically sides of the cage, and these sides can connect to one another. And logically, when you see that this one, the pipe can connect to this one, because it would, when you put them one on top of another, they would be continuous, and it makes sense. Also, this one can be connected to this one, and so on. So this is what I described is actually already the rule that we need to define for Monoceros. There is a super useful component now called modules suggest rules from geometry. The thing is that you can define the rules in a different way. You can draw a line and say, okay, now this is a connection. You do that using a component that is called explicit rule from curve. You can use points that define everything and so on. There's a lot of ways how can you define the rules, but this is a very automatic way of defining a rule. So if we look here, I flatten here because they need to be put into one bucket. If you look here, that you see that now there are rules. This would be a more readable if this was not just a number. So I will concatenate here and make the names a little bit more readable. So I will call them all of the module number. So I will do it like this. Now they are nicely named module 6 and so on. So now you see that there are rules that say that module 0 with connector 2. So let's see which one is module 0. It should be somewhere here. Module 0, I don't really see it. Yeah, it's this one, module 0, and its connector number 2 can connect to module 1, connector 5. So this one, the top, can connect to module 1, connector 5. So I need to find which one is module 1, connector 5. It is this one. So, and it's true. This one connects properly to this one. So that's fine. This is what the rules are basically telling me. So that's awesome. And there is one special thing for those sides, for those connectors that don't have any geometry, any logical way to connect to something else. We call them indifferent. This is also something that is new for Monoceros. Indifferent means that they don't care who the neighbor is, as long as the neighbor also doesn't care. So you can think that this side can connect to either this side or this side. It doesn't really matter. In this setup, the only thing that matters is on top and bottom, and the sides, they can connect whatever they want. And this is actually the indifferent rules. And you see, for example, module 0, connector 0 is indifferent, module 0, connector 1 is indifferent as well. So now I've got two sets of rules. Ones are those explicit rules, ones are indifferent rules. That's fine. I will just create, put them together into one bucket. So I'll put them like this, flatten, and that's my rules. I also have the modules. The modules are here. So I will take the module thing here, floating parameter. And the one thing that I'm missing is the envelope. And the envelope can be, for example, this. I will take this as a geometry. So like this, geometry, set one geometry. Also, I will, for simplicity, I will use a convenience component called slice geometry. This is very tricky, and in long tutorials, I always discourage people from using this. I also explain why in the user manual, but if you know what you're doing, it's fine to use it. You see that it gives you certain points. Those points can be then used for defining slots. And with the slots, we can do a lot of things. I'm not going into details, but what you can define either slots that allow placement of anything, or you can define slot or many slots that define placement of specific modules, and you can distribute where certain modules can be and where they cannot be. So I will just define slots that allow placement of anything. I also need to define how big it is. So now you see that I've got a lot of slots here. The slots are white, which means that when they are white, they allow placement of anything, any module. The purpose of wave function collapse, the purpose of Monoceros in general, is that we want to define, we want to take slots that are non-deterministic. They allow placement of more modules, and we want to turn them into deterministic, which means they only allow placement of one specific module. So this is what we need to do. I will hide everything here. I will only keep this. And there is a solver inspired with Kangaroo. In Kangaroo, you also have a component that is called a solver. You input things, it does something, and it gives you the output. So we do the same. We've got the Monoceros WFC solver. This is the moment where the wave function collapse is happening. We put the slots here, we put the modules here, we put the rules here, and then we hope it finds a solution. It also can not find the solution, and we will see. If not, then I know what to do, fortunately. No, it didn't find the solution, but it's good to show you what does it do. So now you see that it gives you, as the output, it gives you a new set of slots, and some of them are green. The green ones are resolved. Those are deterministic. They can contain exactly one piece of geometry, one module. The white ones, they are completely untouched. They still allow placement of everything, and they're very dark gray ones. The darker gray, the closer they are to the solution. So the problem is that sometimes it's impossible to find a solution because the envelope has an improper shape. For example, if all your modules consist of 5 slots, and if your envelope is narrower than 5, you cannot find a solution. It's impossible to place modules into a small envelope. So I know why this is. It's the method that I used to fill in the envelope with the slots, and I need to change it to a different fill method. And I will only take the slots that are completely inside of the envelope. And I think that this should already find a solution. It told me that it failed to find a solution within 10 attempts. Let's have a look into the report that it gives me. Monoceros is giving very, very detailed reports. So when something doesn't work, you can always read the error messages here or here, and all the components, they give you very, very detailed reports. So I know that it failed to find the solution within 10 attempts. So it's probably not that easy to find the solution. And it tried 10 times. So let's say it can try 50 times, and maybe it will find a solution within 50 attempts. And we were lucky. You see that it did find the solution. There is no error. It tells you that Monoceros WFC solver found the solution. It needed 14 attempts. It took 1.4 seconds. And you see that there's 3,211 slots, which is partly true because the visible ones is 1,600, which is also a lot. Imagine that you would have to place 1,600 modules manually, which is a huge job. So now we have slots that are resolved. They're all green, which is good, but we still don't see the geometry. So there is another component that is called materialized slots. That basically takes the deterministic, the green, the good slots, the resolved slots, and places the respective geometry inside of the slots. So the respective modules. So we've got the resolved slots, and we plug in the modules, and you see that it filled the result, the envelope with modules in a meaningful way. You see that everything is continuous, and maybe we can bake it now. So I will just create a new layer here like this, and I will bake it. Another cool feature about this is that it bakes everything as blocks. So you can double click and change one module, and it changes all of the modules afterwards. So, but anyway, what I want to show you is that if I now take the thing here and break it into geometry and join, you will see that it makes continuous curves out of those individual modules, out of those simple things. So that's the demonstration for now. I'm already 6 minutes beyond my time. Again, I would like to invite you to the Ultimate Monoceros online workshop that is taking place next week. And if you register with the discount code McNeel21, you will get 21% discount. And let us know also what do you think about Monoceros. We are always interested in feedback. And Monoceros is also being developed rapidly. Almost every single day, I'm publishing a new version with improvements and fixes. So also make sure that you always use the latest version, which is 1.2.4.1 right now. That's it from me, and I would like to hear your feedback. Thank you.
Excellent, Jan. Many thanks. It's amazing what you've been doing. And yeah, many people are thanking you on the chat. Also, Thomas Letonen says that this is really amazing, that he will definitely test Monoceros and try to implement it to structural engineering and architecture. And Eva has been adding the websites of the workshop and of Subdigital, together with the discount to the 21% discount you offer on this workshop. I hope many people will sign it. Let's see if there are no questions.
Well, that's kind of disappointing. I would really like to invite people, if they use Monoceros, if you use Monoceros, please send us your projects. We will gladly publish them. Also, this helps us to somehow promote Monoceros and keep the things going. We've been teaching Monoceros at universities. I know that organically many universities adopted Monoceros already. We are available for teaching as well. So let us know. We would like to communicate. We are giving out this to the community, and we would like to know how does it help and if it's useful.
Thanks for the. Okay, yes, one question is coming. Dominic Reisak asks, what's the difference between Monoceros and WASP?
Yeah, that's a very, very often question. I've never used WASP myself, but I know that it's been around and it's quite well made. The major difference is that WASP is basically simulating a growth. It's also a discrete algorithm, but it's growing. It's starting somewhere and it's growing and growing. And we've been doing that for quite some time. And the problem was that when you make a growth aggregate, it usually creates like antlers or branching structure, and it never reconnects. I know that it's possible when you are smart with the design of your components, but and the grid, but you need to plan it ahead. With Monoceros, it naturally creates rhizomatic structures that are not only branching and bifurcating and creating more and more options outside, but also it reconnects, it creates closed loops very naturally. And that's one thing. Another thing is that it always fills the entire envelope. So it never leaves any blanks unless you explicitly want to. So this is also possible. And one of the experiments that I've been doing with Monoceros now is that you can actually use Monoceros to actually simulate growth, but naturally it's not a growth algorithm. It's a complete fill algorithm, you might say, but you can use it for growth, and it's actually quite efficient because you can keep adding modules to an existing aggregate. And Monoceros tells you what are the options left for you, what can you do the next, so that you don't completely break your setup. So you can simulate growth with it, but ultimately it's not meant for growth, but for completely filling certain space. And as you can see on my background, this is also made in Monoceros. This is something that you cannot do when you just use a growth algorithm, because there would be a conflict somewhere sooner or later.
Nice. There is one of the viewers, Gani, that says, I'm late. Okay, you can, again, on this same link, you can watch the webinar since the beginning. Then Lorenzo Glielmi thanks you. He says, it was an engaging talk. I'd like to use it in structural engineering and architecture.
I can comment on that. Monoceros is good for structural engineering, but also it's kind of important to say what Monoceros is not. Monoceros is not directly an optimization algorithm, but you can use it as a part of an optimization pipeline. And what we see as the greatest potential of Monoceros now is when you combine it with other techniques. And this is because it basically takes away the failing options. So if you know how to optimize your structure, you can use Monoceros to actually keep only the viable possibilities for you. Also, another thing that it's not meant for, like, the rules that you define with Monoceros are connection rules, local connection rules between the two immediate modules. You cannot define something that is far away. So you cannot really say that I want to define something, I want to put an aggregate together where I've got this module and very close, there is the same module. It's impossible because they are not really, you cannot define that something should be 5 modules away. Also, you cannot decide how many pieces do you want to use. But all of these things are possible when you combine Monoceros with other tools or techniques. And we see it in our practice that it's very powerful in combination, and when you use it as inside of your pipeline rather than the only sole single tool to use.
Any optimization plugins you recommend?
It should work with all of them. It even should work with Galapagos. It's very parametric, so there is no special feature that would make it somehow complicated. So we also believe that it also should work with all the advanced things like putting stuff online or inside of other programs. So it should work with all of them. In our practice also, even though I'm promoting a plugin here, we try to use pure vanilla Grasshopper as much as we can, because there are many plugins that do things that you can very easily do without. And we try to keep things independent from other people's work. And also that's the idea behind Monoceros as well. It's only offering tools that are otherwise unavailable in pure Grasshopper. So anything that you can do in pure Grasshopper, you need to do in pure Grasshopper. It's not part of Monoceros.
So you control your own algorithms.
Exactly.
Okay, more questions. Yeah, Radnotsi asks if it's possible to make an hexagonal grid.
Yes and no. right now it has to be an orthogonal pattern. So all of the grid cells, they are cuboids. But technically or logically, with the wave function collapse, with anything that Monoceros does, you can not only it would be possible to have all sorts of grids, and they don't have to be homogeneous either. It could work on any graph. So you could have a triangle next to a pentagon next to whatever. But right now it's not, because the logic behind is that the reason why we didn't do it is that we wouldn't know how to make it accessible to people to use, because hexagons are fine, but what if you want to use some other shapes? Or it would be very difficult to define all the geometry, to define all the modules and all the rules. Right now, it's super simple to use. We decided to fight this orthogonality with the possibility to create modules that span over more cages. And we also have, you can see it on the website, we have examples where you almost cannot see the grid itself. And when it comes to hexagonal grid, I do have an experiment, an example that I made that you can actually tweak the grid to actually place hexagons. So if you are smart with your modules, they could be hexagons, and you can basically fill in a hexagonal space. But I don't know, for most of the cases, we think that it's more accessible with something that is easy to grasp.
Okay. Thanks. One more question. This is a bit generic from Khaled Tisset Pro. How can this plugin help us in 3D project designs?
Mm-hmm. That's a very, very good question. And this is something that I have to admit that we got a little bit too excited about the algorithm and that it creates really awesome results. But it took us a while to realize what this is all about. And now I think it's even more powerful than I thought at the beginning. This actually allows you to design your things in a constrained modeling way, which means that you're kind of free to do whatever is not forbidden. And this tells you what is forbidden. And it is sort of an optimization of your design process, because there are obvious things that you've got 5 types of modules and you assemble those 5 types and fill the envelope completely. But also this tells you how to put them together, and you can even interact with it. And you can start assembling these pieces, and this tells you this is still good, what you're doing, and this is not good. And Monoceros is the first tool that I experienced that allows you to do this workflow, to actually tells you what the limitation of your process is, and when should you start doing something else so that you don't end up in a dead end. Another thing that is quite useful, I think, is that it can automatically generate large patterns in a meaningful way for you, which means if you combine it with some basic design process where you design certain parts of your design manually, you decide, for example, you're designing a city and you say, okay, this is the main square, this is a theater, this is a bridge, and make the rest just work, that Monoceros does it for you. So it takes away the burden of creating complicated functional patterns from you, and it can generate them automatically for you. And you still have the control over the things that you care about.
Great. And the last 2 questions, because we are running out of time.
Yes.
Mahmoud Mohanat says that it seems like tissue plugin for Blender. I don't know if you know about that plugin for Blender.
I know. I think it's made by Alessandro Zamparelli, and he's awesome, and the plugin is awesome. But I think it's very different, because the tissue is basically taking mesh geometry and it's like the double mesh. It changes the edges into another mesh. It's really awesome. It's really exciting, and I wish I had time to test it out. But I think it works on the whole thing, and then it makes it more and more precise. Whereas Monoceros is kind of assembling things. It does it in one step. That's a super important thing. That's the difference between WASP and Monoceros. WASP is growing. It's a growth algorithm. Monoceros is not. It happens at one time. But yeah, ultimately, this is not working on any given structure. But it's a very good question because it gave me an idea right now how to actually make also heterogeneous grids accessible for Monoceros. You can use the mesh edges. Yeah, that's it. Nice. That's it. Thank you very much for the idea.
Nice. And the very last question, this is from Lauren Rosser. Are there any modules with physics simulation rules?
You can so you can incorporate physics simulation into the Monoceros solver. It's a bit more complicated, but it's doable. And we tried not really physics, but we tried some analysis. Monoceros allows you to, it can work in a completely automatic mode when it automatically generates the whole thing, or you can stop it occasionally or very often. And you can have a look at what is it doing and measure certain values. Or you can make certain changes and decisions and so on. And if you are into physics simulation and therefore probably structural optimization, you can stop Monoceros at a certain point, have a look, make stress analysis or any sort of physical simulation analysis. And based on the result, you can either change something or make certain informed decision and continue. That's one option. Another option is it for most cases, it really quickly gives you the result. So if you think that it takes 1/10 of a second to give you a result, you can generate a lot of results. Whenever the result is done, you can run the physical simulation and run the analysis. And out of many, many thousands of options, you pick the one that works the best.
Perfect. So Jan and Eva, many thanks for this excellent webinar. Wish you also good luck with your upcoming workshop and hope to meet you soon in person, as we did in the past in some conferences. Have a nice evening. And for you, for the food4Rhino viewers, remember that tomorrow there is a new webinar, this time about point clouds for Rhino, here on our YouTube channel at the same time at 4 p.m. European time. So
thank you very much for having us, and thank you for the attention.
Thank you, everybody.
Thanks a lot.
Have a nice day. Bye.
Bye-bye.
Thank you. Bye-bye.